Just the first thing I want to show that in the last few lectures, it seems that we always talk about mathematics, and we also use just image segmentation as a background or as an application. In fact, there's many other problems. Essentially, it's a segmentation problem. You see, there are many things which is a decision. You need to make a decision between 0 and 1. In finance mathematics, you see, if you make a decision 1, it's an investment. If you make a decision 0, it's a withhold. And so many other things is essentially a 0-1 decision. So here I'm just showing about several other problems that you can think as also segmentation. So essentially here I'm trying to say segmentation is equal to image restoration. Why you say so? Like this is the input image. It's 32 bits. So how many 32 bit 2 to the power of 32? So that means that the range of the intensity instead from 0 to 256 is 0 to, what's the number, to 232? That's a very, very high number, right? So that would take a lot of memory. And then if you want to simplify the image, I just take 3 bits. So instead is the original image. If you want to represent the pixel of one value, you must use 0, 1, maybe 1, 1, 0, 1. So you need about 32 bits to here is a binary number. And so here the maximum number is 2 to the power of 32. And then if you want to simplify the image, I just use the 3 bits. So you just use the 3 bits. Then you can use a simple truncation that may not produce a good image. So instead of what you do, so here is your input image. You do a segmentation, and this is reducing the image to a 3-bit image. And so in some sense, image segmentation and image restoration is the same. There's another way to think about this one. When we do image segmentation, we see that image, so we have an image U belong to 0, 1. So here is alpha total variation of U and plus half U minus F or input the image square. So this is like we segment. So here is a 0, 1, right? But if you do the same thing, but you minimize U, instead of just taking 0, 1, you take a 0, 1, 2, 255. And then you do the same thing. If you do the same thing, and then what you get? This is essentially the discretized R over F model, right? So here you have R total variation of U half U minus square. So this is nothing else but the quantized ROF model, right? So in this sense, image segmentation is a very simplified version of ROF. So in this sense, you see those two are the same. If you do image segmentation or image restoration, it becomes the same problem. And this is quantized, which means you take the discretized values. And so thus there are many methods to do image restoration. You can, in this way, you can copy some of the methods to image segmentation, and vice versa. If you have a segmentation methods, if you just choose using many labels, and that you can use for image processing. So in this way, image processing and segmentation, in some sense, it's the same problem. It just depends how many labels you use. So here you use 256 labels. Here you use 2 to the power of 32 labels. All right. In such a way, you see a lot of things become very much the same. The continuous ROF model, you can think I use infinite many labels. If I increase the label number more and more to infinite many, and then you come to the continuous ROF model, right? So therefore, in this sense, a lot of algorithms has been proposed for ROF. A lot of algorithm has been proposed for segmentation, even for other things. Using such a connection, I think there is a lot of things you can do. You can really mixing those things together. Another problem is like I give you points. I want to produce a curve. This you can do it by level set, but you can also do 0-1 partitioning. So here is a lot of points. I want to find the curve. Is very noisy points. And then want to find the curve, that's a curve. And here is noisy, and that's a curve. All right. You can use a level set, or you can use 0 partition. Here's a 0, here's a 1. And you determine each pixel, it should be inside, outside. That's a 0-1 switching. And this image looks like a very easy, so simple, everyone can do it. But the industry, there are a lot of things from the industry is not so easy. For example, I show you some of the real images. So, for example, this is we have been working with. So this is a cartoon. So they do cartoon animation, or you're making the movie. I think Korea is also Japan, Singapore. Those a few countries are very good with the cartoon movies, also producing games, all these kind of things. So when you produce a game or the elementary things, you have such a drawing. And then the first thing that you need to find the curves. You need to that's called vectorization. You need to find the curves. After that one, each curve you have a mark of the starting point, the ending point, and the interior point. So essentially, you found how many curves. If you have 100,000 curves, each curve, the first curve occupy first vector, second curve, and then you have a registration of all the curves. And this you later in law. That's the first thing you do if you want to computerize. So essentially, vectorize the curves. That's the first thing. At the moment, still, it's mostly they are still doing it manually. So, which means the person is sitting there, dragging the mouse, and then you mark the start, mark the end. There's a computer program you mark the end, mark the start, mark the end. And the computer do a B-spline interpolation and find the middle point and put those points into the vector. Even you see for the computer game, the software there's layers. So layers means that you have several thousands of curves per frame, and so here is a crucial curve. So they put it in layer 1, and then the second layer, it depends on the importance. You put the curve into different layers. So the first thing is a vectorization of those curves, and this image even looks okay. But for example, there are a lot of other images which doesn't look so good. Yeah, you see like such a kind of image. So I need you to computer automatically vectorize such an image. And this is artists, very often they just draw such a thing. You need to vectorize. So you see, for this one, if you do automatic vectorization, take all the curves, the meaningful, it's not easy. It's not easy. And still, at the moment, a lot of the labs are still just doing manual vectorization. So which means the people are sitting there and doing that. They do it very quickly. We see it. We visited one of the labs in Singapore, and they have such a big plate. And then you have a pen. You have a pen. You don't use a mouse. They have a pen tracking. They can do very, very quickly. But still, you see that if you can automatically do it, And I believe it is possible to automatically do it. Also, I think you see like a documentation. The engineer have a lot of drawings. They want to scan those drawings. They want to vectorize, find all the curves, make the drawing into really like a curved drawing. That's a documentation retrieval. In the library, you want to do a lot of automatic recognition. So there's a huge, if you go to the computer science department, there's a huge number of people working with these problems. But as a mathematician, we can really make the methods, which is more different. So this kind of application looks like a small application. In fact, there is a huge number of industry, a lot of people working there. So by looking from the point of a mathematical view, I think most probably we can do quite a lot with those things. So this is related to the curve and 0-1 partition. Here is we use the Max floor to do the TVL1. And so essentially is using such an idea. The algorithm here we use is very similar to the one by the Dabon-Sigil. But when the image is getting very, very big, and then we use domain decomposition. So Professor Lee is one of the leading experts in domain decomposition. So here, I think what we do more is we really use the domain decomposition. We partition the image into many pieces and do max flow over each piece and do some iteration between them, and we get that one. So this is trying to overcome the memory problem with the graph cutter approach. So here is we do surface construction. So I give you a point clouds. I do partition these. I will talk a little more maybe afterwards. So I partition the domain into four regions. Each region construct a surface and do a few iterations between them. And this is the surface you construct. And this is also 0-1 partition. You have a surface. So inside surface is 0, outside surface is 1. Here we just minimize it's like a geodesic active contour. So minimize the geodesic active contour. So here we try to show that can you really preserve corners. I think mostly in surface, the surface never have a discontinuity. But if you have corners, which means the derivative has a discontinuity, can you preserve the discontinuity of the derivatives? So that's the difference between image and the surface. Image, the discontinuity is crucial. So surface, you seldom have a discontinuity with the surface, but you have a discontinuity with the derivatives. So can you really preserve the discontinuity of the derivatives? Here, I think Professor Lee is also interested in these kind of applications. Very often, so you have a lot of curves. Those 2D curves could come from 2D segmentation, from many other things. And from those 2D curves, can you produce a 3D triangulated surface? This is also, in the end, become a 0-1 partitioning. So this is, you see, you have a lot of 2D information, and you do a 3D 0-1 partition. So which point is inside, which point is outside. You can use a voxel mesh, or you can use a tetrahedron mesh. Right. Here, really a lot of application you need to do this one. A lot of simulation for finite element simulation. Here you see like the brain mapping. You really you have MR data for your brain, and then the doctor knows there's only 4 material inside your brain. Can you really accurately segment those things? And very often the segmentation will be very accurate. If you just do a little wrong, it doesn't work. So this is segmentation. Yeah. Even related to like a surface construction. So what I'm showing, you see that really also like a research one. So here you see that this is some from real application. In fact, I shouldn't be talking about this one. I hope the company doesn't see the video you will post on the web page. So this could be really a huge $1 million project. So essentially, we have they are going to simulate the explosion of the factory facility. So huge factory working with chemical gas. If there is a leaking, if there is explosion, you want to construct your factory such that it's most safe, or the destruction only confined to a small part. And in that way, you need to simulate. If there is an explosion, you need to simulate it. So before you simulate it, you must construct 3D mesh. And the Norwegian company which is doing this one is leading in the world. And so the first thing you do, you scan, use a laser scan of the whole factory, and this is from real data. And due to occlusions, very often you construct a part of the pad, part of the beam, and can you automatically construct this 3D surface from those point clouds. At the moment, they are still doing this one mostly manually. So there is an Indian company. So they have a scan, you construct it, and then you see there is a lot of occlusion. You see half of the pipeline is, and then there is a program which determines automatically. You see here should be occlusion should be patched up in this way, other way, and then you do a manual selection. But then the whole factory really this take a lot of manpower, So I think this is not one company is needing this one. There's a lot of companies. If you go to, there's quite a number of international companies like Autodesk. They are doing this one very well. If you look at the demo, it's very impressive. But if the demo case doesn't cover your situation, doesn't cover your demand, and this becomes quite complete. And this is also huge activity in the computer science department. If you Google the so-called reverse engineering, some of the software works very well. They just take a video photo of the whole building from the video, and then if the video is moving, they can construct the depths. So and then they have a very noisy cloud, and then they construct the surface to the whole building just from some video things. You see, like this one, there's some fundamental things is about zero-one construction. But here, mostly they call reverse engineering, because for this kind of factory, they want to assume, you see, the surface is either part of a pipeline, or is a part of the box, or is a part of a plane. So the geometry of the surface, you only have several choices. They don't give you, so for this case, you only about maybe a cylinder, boxes. So here is a cylinder and boxes. So here is like a boxes, or the surface must be part of a plane, or part of a cylinder, or part of a sphere. So you only allow several possibilities of a geometry. And then if you do this one, so can you really do it very well? Can you do it very well or not? So this is also related to the surface construction application. So it's really not very easy. Even the testing we have been doing is very easy. There's a lot of high-tech company, and they really need this one very urgently. So really, you see, like that surface construction, really they wouldn't hesitate to pay you several $1 million to buy your software if you can really do it automatically for them. If they just they just scan the whole factory, give the data to you, you will reconstruct and give them the geometry. Even scanning one factory at the moment costs about nearly $500,000. Just scanning the whole factory, and then after scanning, you need to process. So this is a real business now. Like also this one. So we have seen this one, so you know what's a construction, right? So this is a construction, and this one. So also Professor Lee we have been discussing this one. Also we use a graph card, so the memory is not enough. So we do domain composition. So you have a 3D mesh, and we decompose to 100 small blocks, and do a construction each blocks, and then use iterative methods to do some kind of boundary condition matching. So here I think there is a real need for domain composition. There's a real need for domain decomposition. So here we use similar to what the Myung, the method I think Myung was talking about. They're very good for texture. So here we are doing texture. So essentially, I think the texture we do here is that we also use a Gauss transformation. So Gauss transformation, so every image, so the Gauss transformation is adding more vector value into each pixel. So essentially, you are processing, segmenting a multi-channel data. A color image is 3 channel. If you're adding all the Gauss transformation, it depends on how many scales you add and how many directions. So here normally we use about 3 scales with the 4 directions. So that means 3 times 4, there's the Gauss transformation for gray image that produce another additional 14 values per pixel. If it's 3 colors, you multiply another 3. So that means you see over each point you have a very, very long vector. So essentially how to process that vector data and segment that vector data, so that's essentially how you can extend it to texture images. So everything here we did was by using Gauss transformation, but we use a few more scales. So here you see the other application. Here you have a vector field. See, you have a vector field, or this is motion in an image, or you want to segment a vector field. So a vector field essentially is a color image, right? 3D vector is RGB, 2D vector you only have 2, and you have a long vector. So that's so how do you segment a vector or process a vector? That's essentially processing vector image, like a seismic. So therefore, this is essentially you try to process the vector and look at the vector distributions. So what I'm just trying to emphasize is that so it's not like also tracking. You see, tracking is also segmentation. So what I'm trying to say here is that it's not segmentation. You need to use this kind of a 0-1 partition, but there are many other applications you can use the 0-1 partition. So mostly if we can combine good mathematical ideas with the real applications, so very often you can, I think you can produce rather good ones. And some of the applications is really industry urgent. So the industry really needs it. They want a solution. They want to solve it. So because we are getting better mathematical methods, and very often some of the problem which was not able to solve just a few years ago, maybe is just using the new method we develop, and then you can solve it. Especially the computer science researchers are doing a lot, and then if you look at their demo, it's very often very impressive, unbelievable. But sometimes you see some of these methods, you see the demo is good, but if you use other data, it may not be as good. But we mathematicians, we are used to emphasize the methodology, but we often don't produce so good demos, because we want to have a method which works for more general problems. But if you can really combine, sometimes you really produce very good result. Also more often, like this kind of research, when we do more fundamental research, we found many of the methods are essentially related. You can interpret it in a very simple or very easy way, and that's make people to kind of improve the methods much better. Yeah. So here I'm just trying to say a little more about what kind of other applications. I think there are a lot of industry are strongly demanding all those things. Yeah. Also, one thing I have for my lecture, I have put it. I have put it. You see all the lecture material into the internet, so you can download it. So I have put it here. www. And here is a small letter cast, and then here is just capital TIE zip. So all the lecture PDF file which I have been talking in the last 2 weeks, so I have put everything here. Also, I have put it all the related papers, because we talk about a lot of things. Many of the things are coming from us. This paper there, that paper. I have put in many of the papers there, like some of our own, most of them own paper. We also put it like a Changverse or Xue-Cheng. I don't know if I put it the Shambo's paper or not. Yeah. So you can get it from there. And also, if you have anything about what I've been talking, so send me email or send Professor Lee email. So this is my email address. .no. So there are 2 PDF for the lectures. The rest is for the papers. The PDF for papers. Yeah. So if you have questions, ask Professor Lee or send me email. So I will be happy. To be able to answer you. And for the last part, so I'm thinking just talk about 2 methods. So yeah. Oh, so here, yeah. Before maybe we switch, we talk a little bit more about this surface. The surface construction, here I forgot that. Here is mostly done by one of the PhD students on Wang Min. He was mainly supervised by Professor Desheng Wang, and he was together with me and with my PhD student Aggie Bai, also another PhD student from Singapore. So here, so I'm trying to show, so how do you use a surface construction? You have a point clouds. So here the red point is the point clouds. You try to construct a surface, especially triangulated surface, passing through all those either passing through all the point clouds or to be as close as possible. So what we do is that we construct a tetrahedron in a huge cube which cover this one. It's best those points is the vertices of the tetrahedron. So afterwards we determine if it's far away, we know that this must be the exterior of the surface. If it's far away inside, it must be interior. So here the gray region must be exterior. Here the yellow region must be interior. The surface must be somewhere here. So essentially you need to draw a line. So where is the 0, where is the 1? And we use a graph cut. So we minimize the surface. We also minimize. So here is you minimize the surface area. Here, which means that the surface should be closest to the point cloud. So this is a distance. So we try to use a graph cut to minimize this one. In fact, this model was first proposed by Hong Kai Zhao and Usher, and this model has become very popular. Now you see we have gone through all the models. In fact, this is nothing else but the geodesic active contour with D as an edge detector. So in this way, it looks very simple. It's just a geodesic active contour with D as edge detector. So where D is the smallest, you put that one as an edge. That's the surface you produce. Do you know what's the meaning of this D? D is the distance to the point clouds. So for arbitrary point, you calculate the distance to these point clouds. So therefore, this D equal to 0 at the point clouds. Here you want to find the curve or surface such that D is the smallest. If you don't regularize, so this one must go through all the points because D equal to 0 there, and then you find. So essentially we just augment it a little bit. So here is by using priors. So here I have a 1, here you have a 0, and this part we use a priors. So we also label must be 1 here, must be 0 here, and then minimize those things in the interior. So the first is the data and the mesh, and then you determine the interior, exterior, some pairs. And then you do a graph cut, construct the graph. And then you do a graph cut. So therefore, that's an interior, and this is exterior. So there's a 0, 1. So originally, the red region, you don't know is a 0 or 1. You don't know. But once you do a graph cut, every tetrahedron you know is a 0 or 1, and then you know where is interior, where is exterior. So clearly, and then you just extract the surface, and then you get it. Right? So you just extract the surface, so this is the surface you get. Because you have a 0, 1, 0 inside 1, yeah. So, and this way, this is for this, you have a point clouds, you make a very large cube to include the object, construct a tetrahedron, and then you see the inside, outside, and then you try to use a graph cut to determine so here is all the surface you constructed. But there's another thing we want to emphasize is how do you construct open surface? You see, if you have such a domain, if this curve we call it the open curve. Open curve, you see that open curve, such a curve, there's no way to do a 0, 1, right? There's no way to do a 0, 1 open curve. You can do a 0, 1 partitioning only if the curve is a closed curve, inside 0, outside, right? But so that's the idea we use is very simple. So essentially, this curve in the square domain is not a closed curve. But if I put a red curve here, in this inside this region by the red curve, you can use the 0, 1 partition. So that's essentially what we do. So for the open surface, for the open curves, we always try to put a small region around that curve and do 0, 1 partition and moving these two ends to really to fit your data. So in this way, the open curve doesn't differ from closed curve. But then the only thing you need to do is that you need to move this boundary part up and down to fit your data point. So that's one thing we want to emphasize, because others open curve seem to be a problem for surface construction. That's another thing we try. So here, so essentially this is the open surface. You get here the open ones. So essentially you see that we use some way to move this boundary part in and out to fit the point clouds here. And then you can construct every open curve. Every open curve. Here is all open surfaces, so you can use a 0, 1 partition. So all those are still, you see, and moreover, traditionally in the literature, mostly they can only construct surface, you have a 0, 1. But if the surface has a triple junction like this one, so here is several surfaces passing through the same curve. In this case, two label is not enough, right? If a 0, 1 label is not enough. In this case, you have outside 0, label 1, label 2, label 3, label 4. And then you need to use multiple labels. And then you can use what we were talking. Usually we have a two-phase segmentation, we have a multiple phase segmentation. Using our technique, you can really do this kind of thing. So it's here like a label 0, 1, 2, 3, 4 labels. You can segment this one. Also for this surface, it's not closed surface. Mostly you have a label 1 is down, label 2 is up, and label 3 is inside. So in this case, you need 3 labels. And for example, this kind of a surface is still difficult in the literature for people to segment it. But using all the techniques we have been developing here, you can do this one easily. And then the other thing is you see domain decomposition. Professor Lee, so really hope we can do something in this area. So Professor Lee is one of the leading research in the area of domain decomposition. So here we really use it to do surface construction. So you construct a surface here, and then you, do some kind of overlapping. It's very similar to partial differential equations, so I don't talk about the details. So here is you see we partition the domain into two subdomain, construct surface here, and do several iterations. There will be no cracking here. Otherwise, you do discontinuities here. All right. Here is what you have seen. So we partition the region into 4 regions, construct a surface in each region, and then do several iterations, and you get a surface. Because this is for a lot of the data scan. For example, the factory data scan. So do you know how big is just a small portion of the factory of the point clouds? You know how much is the memory? There is a whole factory. We just got the data for a small portion. Even for a small portion in the disk, it take about 32 gigabytes just to store the data points. And there's no computer you can memorize these 32 gigabytes. And then what you need to do, I guess, as domain decomposition is you do section by section. It's the only way you can do it. Even that 32 gigabytes is just a small portion of the factory. It's not the whole factory. So therefore, you see this kind of, you see like this one we have a 4, and that one we have a 2, that one we have a 2. But another very good thing is that, for example, this is a non-orientable surface. This is called the Mobius surface. This surface is it goes up and down. The normals you see for this surface there's no way to do 0-1 partition. There's no way to do 0-1 partition. So what we do that we partition the domain into 2 regions. So even this one, even use the even you use the open curve technique, even you use this idea, it's not possible to use a 0-1 partition to construct this surface. Right? Even you use this idea. So phi equal to 0, phi equal to 1 here. It's impossible. So what we do, you partition the surface into 2 parts. And this part you have a 0-1, and this part you have a 0-1. And here you let it to match together. You see both of those 2 subsurfaces is orientable. But when you put together, it's not orientable, and this is what we construct. So this is domain decomposition. And there are some more points. When you solve a partial differential equation, you don't have this one. But for this application, you see domain decomposition has more advantages. More advantages.
Let me have one tricky question.
Yeah.
We can reconstruct the Klein bottle.
Sorry?
Klein bottle.
What's that?
Klein bottle.
Oh yeah, that's the next one. Yeah, very good. You see that you have people asking questions from. So here is a Klein bottle. So essentially, this Klein bottle, there is no 0-1 partition. So essentially, we cut it here. The outer part have a 0-1 partition. Lower part have a 0-1 partition. We put it together with 3 parts. You construct a Klein bottle, right? So this, you see, this advantage of domain decomposition never shows up in partial differential equations.
That's not 3-dimensional.
No, you can solve a 3D PDE, right? You can solve. Here is so essentially we are solving a 3D PDE, right? So this one, you see that if you really do this one, you can come. This is very good. Why do you ask this question?
Because it's realized because we can realize the 4-dimensional in the computer and memory spaces are enough. Then
right.
And then you already said so division is reduced to 3-dimensional. Then they combine them we can make the 4-dimensional surfaces also.
That's why. So I think for domain decomposition, these kind of things maybe should be further explored. So here you make a domain decomposition, you not only reduce the cost, you overcome the memory problems, and then you get some more advantages. Yeah. So here is we are trying to use other method to process surfaces, preserve corners. I think non-local is still very good, but the new method we propose also quite okay. We are still doing testing on this one. Yeah. So this is just trying to show that you see this kind of ideas also has some other applications. So what we may do, let's take maybe a 15 minutes break, and then we continue some more, and then we finish today. Okay, let's take a break now. Yeah.